This is the video for section 3.4. In this one, we're going to talk about linear and angular speed. This goes back into chapter 3 where we were talking about arc length and the area of a sector. When we talk about linear speed, what we mean is that if we have a point that's moving around the outside of a circle, we want to know how fast it's actually going along that path. What we're actually going to do is use a formula that I know you've seen before. This is the one that says distance equals rate times time. In this case, our distance is the distance moving along the outside of the circle. That's the same as the arc length s. The rate is what we're calling the linear speed. We're going to use v to represent that. And then the time is just going to be t. So instead of d equals rt, we're going to have s equals vt, and if we want to find the linear speed, then we can solve this for v, and we come up with this formula right here, v equals s over t. The only thing to remember with this one is that s is talking about the arc length. So to use this formula, let's say that our point P is on a circle with a radius of 10 centimeters. It's moving at a constant speed around the outside of the circle, and it goes through an arc of length 24 centimeters in 15 seconds. And we're wanting to find the linear speed of the point P. If it's moving through an arc of length 24 centimeters, that's our S. In other words, that's our distance. And our time is 15 seconds. All we have to do to find the linear speed is divide our distance by our time. That would be 24 centimeters divided by 15 seconds. And these problems were a little bit picky about including the units. If you include the units when you're using the formula, then you'll have them there to put in your final answer. If we divide 24 by 15 and round that to one decimal place, we get 1.6. And then our units is going to be centimeters per second. The next thing we're going to talk about is a different type of rate, and this is called the angular speed. What this has to do with is how fast the angle is changing with respect to time. Again, we've got our point P that's moving around the outside of the circle. That means that we can look at this angle, which is actually POB, but we can call that angle theta. What we're looking for with angular speed is how fast theta is changing. We just take the amount of angular change and divide it by the time. This is a lot like what we did with the linear speed. In that formula, what we had on the top was the arc length, and we divided by the time. This time, since we're trying to find the speed that the angle is changing, what we're going to have on the top is the angle. It's very important that you remember for any of these formulas, your angle theta has to be measured in radians. Let's look at another example where we're finding both the angular speed and the linear speed. In this one, we've got a circle with a radius of 10 centimeters, and our ray OP completes one full revolution in 40 seconds. In other words, the point P moves one time around the circle in 40 seconds. And first of all, we're trying to find the angular speed of the ray OP. One thing to remember with these is that if we're talking about revolutions, if we're thinking about the angle measure in radians, one full revolution is equal to 2 pi radians. For our angular speed, we're taking the angular change, theta, divided by the time. If it completes one full revolution, then our theta is 2 pi radians. We're dividing that by the time, which is 40 seconds. To get an exact answer for this, we're just going to simplify this. That would simplify to pi over 20. And this is going to be radians per second. The next thing we're going to find is the linear speed of the point P. So this time we want to know how fast P is moving around the outside of the circle. Let's go back to our formula for the linear speed. That was V equals S over T. Now these two formulas are connected. Remember that S in our arc length formula, S is the same as R times theta. So we could replace this S right here with R theta. And then if you compare this to our formula up here for the angular speed, we already have the theta over t, where we found our W That's the same as the theta over t. So we already have this part of the formula that we can plug in. We also know our radius is 10 centimeters. So we have that for the r, and then the theta over t we can replace with our w, which is pi over 20 radians per second. Now to get an exact answer for this, let's take the 10 times the pi over 20. We can simplify that part. For the units, we're going to keep the centimeters and the seconds. Remember that radians isn't a unit like other ones, so we can actually just leave off the radians and get centimeters per second for our units. And if we simplify this a little bit and cancel out a 10, we actually get pi over 2. Now this problem asks for an exact answer. To get a better idea of how fast this is actually moving, we could use an approximation for pi to get an approximate answer for this. If we round this to 1 decimal place, this would be 1.6 centimeters per second. Then the last question is to find the distance traveled by the point P in 16 seconds. Remember that P is traveling around the outside of the circle, so the distance traveled by point P is really the same as the arc length. And remember, our arc length is s. If we go back to our formula for the linear speed, we actually know the value for the linear speed is pi over 2. We want the time to be 16 seconds, and we're trying to find the arc length s. So if we go back to this formula, we have the v and we have the t, and we're trying to find the s. I'm going to plug in pi over 2 centimeters per second for the v and 16 seconds for the t. And then I'm just going to solve this for s. So to do that, I can just multiply both sides of this by the 16 seconds. That will give me the s by itself on this side. My seconds cancel out. I can cancel out units just like I cancel out numbers. And if I'm going to simplify this, I've got pi times 16 on the top and a 2 on the bottom. That's going to simplify to 8 pi. The only unit I have left is centimeters. This would be my exact answer. An approximate answer rounded to 1 decimal point would be 25.1 centimeters. Let's look at a couple more examples. In this one, we've got a belt that's running a pulley. The radius of the pulley is 6 centimeters, and the speed it's going is 80 revolutions per minute. Remember, we said that 1 revolution was equal to 2 pi radians. So if we're looking for the angular speed, that's how much the angle is changing divided by the time. What we need to find for our theta is how many radians this would give us. 1 revolution is 2 pi radians. That means that our theta is going to be 80 times 2 pi. And then it tells us the amount of time. This is per minute, so we could make our time equal to 1 minute. That gives us radians per minute. Now the question was actually asking for the answer in radians per second. So now we need to convert the minutes to seconds. To do that, we can use a unit fraction, and we want the minutes to cancel out. So on the top of this, I'm going to put 1 minute, and I want to change it to seconds. So on the bottom, I'm going to put 60 seconds, since 1 minute is equal to 60 seconds. So my minutes cancel out. That means I'm taking my 160 pi and dividing it by 60. Now this one didn't say whether it wanted exact answers or approximate ones. So I'm just going to leave this as an exact answer. If I simplify 160 pi over 60, I end up with 8 pi over 3. And my units for this now are radians per second. Now I can find the linear speed of the belt. What that's asking for is how fast the belt is going around the outside of the pulley. Here's my formula for the linear speed. Again, in this one, I already have the theta over t. So I'm just going to change this s to r theta. And then I'm going to replace the theta over t with my angular speed. My radius is 6 centimeters. My angular speed is 8 pi over 3 radians per second. If I take 6 times 8 pi over 3, that's going to simplify to 16 pi. And then again, when I've got all these other units, I can just forget about the radians. So my units here would be centimeters per second. 16 pi is approximately 50.3. In this one, we've got a satellite in orbit above the Earth, and we're trying to find the linear speed of the satellite and approximate the distance the satellite travels in a certain amount of time. For this one, I'm going to draw a picture. Here's the Earth with the radius of 6,400 kilometers, and then I've got the satellite in orbit above that at a height of 1,600 kilometers. So the distance from the Earth up to the satellite is another 1,600 kilometers. If I'm thinking of the circle that is the orbit of the satellite, then my total radius of my circle is the 6,400 plus the 1,600, which would be 8,000 kilometers. Now what I'm trying to find is the linear speed. That's the v. So for this one, it might help if I find the angular speed first, because I know that this takes 2 hours to make an orbit. An orbit is the same as 1 full revolution, so it takes 2 hours to complete an angle of 2 pi radians. That means my angular speed, the theta over t, is 2 pi over 2 hours, which would simplify to pi radians per hour. Then if I want to do the linear speed, I'm going to change my s to r theta, and for the theta over t, I'm going to substitute in the pi. I know my radius is 8,000 kilometers, so that gives me 8,000 kilometers times pi radians per hour, which gives me 8,000 pi kilometers per hour. Now in this one it said approximate. This is an exact answer. If I'm trying to approximate this, I'm going to take 8,000 times an approximation of pi, which gives me approximately 25,133 kilometers per hour. Now this is a good time to use an approximation because this gives you a much better idea how fast it's actually going. It's a little hard to tell when we're talking about pi being in there, but if we use an approximation, we can see that that's pretty fast. Now we want to approximate the distance the satellite travels in 4.5 hours. Our satellite is going around the outside of this orbit. This is asking us for an arc length. We can go back to our formula for the linear speed and just solve it for s. That gives us s equals v times t. This is the same as distance equals rate times time. We already know our linear speed, and our time is going to be 4.5 hours. We've got 8,000 pi kilometers per hour times 4.5 hours. Our hours are going to cancel, and then we can multiply these three together to get an approximation. That's going to give us 113,097 kilometers approximately.